Now I want to talk about Fano's inequality. Fano's inequality is very important. This is used in channel capacity theorem. Channel capacity theorem is the most important part in this class. With the channel capacity theorem, we have practical channel coding scheme that provides protection against channel noise, and digital communication has become possible. So that's the importance of Fano's inequality. So we have to study this one very carefully. So in this problem, we want to consider the problem of send X, observe Y, and make a guess, estimate, Gy on X. So you send X, observe Y, and then you make a function of Y, and that is your estimate on Y for inference on X. That's the problem. So we have X to Y to X prime, which is defined to be G of Y, function of Y, forms a Markov chain. Fano's inequality relates that probability of error, which is defined to be probability of your estimate X prime, which is equal to G of Y, is not equal to X. So that is the probability of error. PE is probability of error. And then Fano's inequality relates this probability of error with entropy X given Y. What is entropy X given Y? Given Y, it describes uncertainty on X. So probability of error has some relationship with uncertainty on X given Y. So Y is an observation. Using the observation, you want to estimate what X was. So the probability of error has something to do with uncertainty on X given Y. So that's the notion. That's the insight you could bring into this problem. So we already know the entropy X given Y is non-negative. With the equality, if and only if X is a function of Y. So probability X prime not equal to X, probability of error, is equal to 0 if and only if the conditional entropy X given Y is 0. Thus we expect small probability of error for small conditional entropy X given Y. Okay, small p for small conditional entropy X given Y. That's the compact insight that we can bring into this problem. So somehow PE can be related to uncertainty on X given Y. Now, Fano's inequality can be described with this thought experiment. Consider alphabet X, alphabet Y, and estimate on X using Y, which is X prime. So alphabet X has 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. And when X1 is selected, the observation is Y1. When X2 selected, also the observation is Y1. So this is a many-to-one mapping. And 3 is selected, Y2, 4 selected, and the observation of Y2, 5 and 6, the same thing. When you select 7, it is 1-to-1, and you get 7. 8, again 1-to-1, you get 8. So alphabet Y has only 4 elements. Y1, Y2, Y3, Y4. Okay. So that's the observation set, and let's do the estimation. When you receive Y1, you will decide for X1, Y2, X3, Y7, X7, Y8, X8. Or we can use the indexes only. So 1, 3, 7, 8, 1, 3, 7, 8, 1, 3, 7, 8. Having described this example, then whenever you select an input going through this mapping relation, the input set can be divided into 2 different sets, the error set and no error set. So whenever Y1 observed, the probability of error is half, because whenever you select element 2, it ends up as an error. Whenever you select 1, it is no error. What about Y2? Given Y2 observed, 3/4, there are 4 elements, 1 is correct, rest of them errors. So the probability of error given Y2 observed is 3/4. Then we can divide the set of input into 2 disjoint sets. First set, x prime is equal to x. That is those are the cases when you send 1, 3, 7, 8. Now we can consider the error set, which is 2, 4, 5, 6. 2, 4, 5, 6. That's the error set. The Fano's inequality is described by these 2 lines. Entropy on distribution PE, since it is a binary distribution, error or no error, we can describe it with a single parameter, which is PE. So entropy of PE plus PE times log of alphabet size x minus 1. That left-hand side is greater than or equal to the entropy of x given y. So that's the Fano's inequality. And we can have a weaker version of Fano's inequality by having weaker version. So this one here, since it is an entropy, it is smaller than or equal to 1. So it can be upper bounded by 1. So 1 plus this term, and that term is also upper bounded by log of x instead of log of x minus 1. So this whole thing is upper bound to this part. Since it is a larger than this one, it is a weaker version. And move this 1 to the other side and log of x to the other side as well, we get this thing.